Now that we've established some basic properties of tensor products, let's do an example. Let's say A is any finite abelian group, so it's a Z module. We'll show that the tensor product of Q with A is 0. And the way that we're going to prove this is by proving that every elementary tensor is 0. Because the tensor product is generated as an R module, in this case a Z module, by elementary tensors. If we know that every elementary tensor is 0, the entire tensor product is also 0. So let's take any element in our finite abelian group. We know that there exists some positive integer n such that n times a equals 0. And now let's take any rational number. So we have to show that our tensor A, this simple tensor, elementary tensor, is 0. But R is n times R over n, which is also an element of Q. So R tensor A is n times R over n tensor A. And this is n acting, the integer n acting on the element of Q, R over n. But one of the key properties of the tensor product is we can take elements of the ring and pull them out or move them into the other component. So n times R over n tensor A is the same element as R over n tensor n times A. N times A is 0, so this is R over n tensor 0, which is 0. Okay, so what did we do here? The important thing was to use the fact that in the tensor product, R dot m tensor n is the same as m tensor R dot n, that we can move this element of our ring acting on our module element from one component to the other. So what is this really saying when you think about it, though? It's just saying that what do tensors represent? They represent some coset of this submodule D that we used to define the tensor product, that these two elements in the corresponding elements in the free module are in the same coset of D. Okay, so we'll get very used to this kind of argument. So this works in a more general case than the one that we set up here. In fact, all we used was that for any element A in our abelian group, there exists a positive integer n such that n times a equals 0. It didn't have to be the case that our abelian group was a finite abelian group. So the exact same argument works if A is an abelian group where every element has finite order. So you can even take like an infinite direct sum of copies of Z mod nz or something like that. Okay, another example is that Q tensor Q mod Z is also 0 because Q mod Z has this property that it's an infinite abelian group, but every element has finite order, right? Because for any rational number, there exists some number of some positive integer so that you add it to itself that many times and you land in Z. All right, so you can do the following in a similar way. I'll leave it to you as an exercise to work out the details, that Q mod Z tensor Q mod Z is also 0. How do you show that? You show that every elementary tensor is 0, and you can use a similar idea, but the details are a little different. So I'll pause and erase, and we'll continue our discussion of tensor products. I next want to talk about how to define linear functions from your tensor product to some other R module. And we know that we have this nice spanning set for the tensor product, the elementary tensors. We know not only is every element in the tensor product a finite R linear combination of elementary tensors, but in fact is just a finite sum of elementary tensors. Either way, what that means is that every R linear function, L, from the tensor product to some R module P is determined by the values it takes on elementary tensors. So if I specify the values at all the elementary tensors, there's only one way to extend that to the whole module, that you take any element in your tensor product, write it as a finite sum of elementary tensors. And if I know what L does at that finite set of elementary tensors, then I know what it has to do to their sum. All right, but the tensor product is not like a free module. The elementary tensors satisfy lots and lots of relations between them. So you can't just specify any values you want of L m tensor n, values of L at these simple elementary tensors, and expect to actually get an R linear function. The values you specify need to respect the relations among the elementary tensors in your tensor product. So here's an example for you to think about. If you try to define f to be a function that takes an elementary tensor m tensor n to m plus n, then you'll see that this is not actually going to give us a linear function from the tensor product to anywhere. So what goes wrong? Well, negative m tensor negative n, that's the same element as m tensor n. This is an example of a relation satisfied by elementary tensors. Why? Because you can pull out 1 minus 1. This is minus 1 times m tensor minus n. And then you can pull out the other minus 1 and see that this really is m tensor n. So that means since m tensor n and minus m tensor minus n are the same element, f needs to do the same thing to that element. But f of minus m tensor minus n is minus m plus minus n, which is not usually the same thing as m plus n. I mean, that's only going to be true if 2m plus 2n is 0. Right? So this does not usually hold. You can't just specify values of a function at elementary tensors and hope that you're going to get an R linear function. I mean, you might get lucky, but most of the time you won't. There just is no linear function taking a set of values that you prescribe at all of the elementary tensors. All right, so given that, how do we actually construct linear maps from the tensor product of two modules to some other R module? We can't just specify any values we want at elementary tensors. And the answer involves really thinking about what the tensor product is supposed to do. The key thing to keep in mind is that linear maps out of the tensor product correspond to bilinear maps out of the direct product m cross n. So how do you construct a linear map? Back up and find a bilinear map B from m cross n to P. So this will be a big theme of understanding tensor products. So at this point, I just want to point something out that we're not going to focus on here, but you should be aware of, which is we've been talking all about the tensor product of two R modules, but you can completely analogously define the tensor product of a finite collection of R modules. And so what do? You can just extend these definitions to allow more than two factors. So you can take the tensor product of R modules M1, M2, up through MK. And for a little more detail on this, see page 11 of Conrad's notes, but this is not something that we're going to focus on here. Okay, so I'm going to pause and erase, and then I'll go through some basic questions that you might have about working with tensor products. I next want to talk about some things that Conrad refers to as beginner questions about tensor products. And a big theme here is going to be understanding tensor products in terms of bilinear maps. So first question, what is the elementary tensor m tensor n? Here is an answer. It's the image of the pair m comma n under the canonical bilinear map tensor that goes from the direct product to the tensor product. Maybe that's not so satisfying though, because what do you do with that information? So another way to think about it that's not exactly a definition, but is a main property to take advantage of is it's the element of the tensor product where the linear map L from the tensor product to P takes the same value as the bilinear map B from M cross N to P. So what does that mean? You start with a bilinear map. The existence of the tensor product, what it means to be a tensor product, means there's a linear map corresponding to it. So you start with your bilinear map. You have your pair m comma n. And L of this M tensor n, whatever that is equal to B of M comma n. So what is M tensor n? It's the thing that you put in to this linear map to match the output of this bilinear map. All right, so given that description, what does it mean to say that an elementary tensor, M tensor n, is equal to 0? Well, it means that every bilinear map from M cross n to anywhere vanishes at the pair M comma n. And this is a helpful thing to think about. In particular, this gives a nice way to see that an elementary tensor is not 0. If being 0 means that every bilinear map from M cross n vanishes at M comma n, then to see that it's not 0, all we need to do is find one bilinear map, B, from M cross n to P, that does not vanish at M comma n. That means that M tensor n is not 0. All right, so now we know what it means for an elementary tensor to be 0. What does it mean for the whole module to be 0? Well, it means that every bilinear map from M cross n vanishes at the pair M comma n for every pair that you could choose. So that means that every bilinear map from M cross n is identically 0. That there are no non-trivial bilinear maps from M cross n to anywhere. So a tensor product being 0, you can just think of as a statement about bilinear maps from your direct product M cross n as a set to anywhere. All right, let's see an example of this, building on the example that we did earlier in this video. Let's say A is a finite abelian group. Every Z bilinear map B from Q cross A to any Z module, any abelian group P, is identically 0. Let's see why this is true. Not surprisingly, this argument is going to look almost exactly like the one that we already used to show that every elementary tensor in the tensor product of Q and A is 0. Because what's really going on here is the same thing. So let's suppose that B is a Z bilinear map from Q cross A to some Z module P. Let's take A to be an element in our finite abelian group. And we know that there's some n, a positive integer, such that n times A equals 0. Then we're going to show that this bilinear map is identically 0 by showing that B of R comma A is 0, where A is any arbitrary element in here, and R is any rational number. So the important thing is just for every A, we have an n so that n times A equals 0. So what is B of R comma A? Well, it's the same as B of n times R over n comma A, because these are the same rational number. But then if this is a bilinear map, we can move this n from the first component to the second component. So this is B of R over n, comma, n times A. But that's B of R over n 0, which is 0. So what's the thing that made this work is that the same way that we can move the action of a ring element from the first component to the second component in an elementary tensor, we can do the same thing in this bilinear map. OK, so I'm going to pause and erase, and I'll talk about one additional one of these questions from Conrad's notes. Let's briefly talk about one more of these beginner questions about tensor products. We've talked a lot about elementary tensors, but I really want to emphasize that not every element in a tensor product is an elementary tensor. So you have a sum. You just have an arbitrary element of a tensor product, m1 tensor n1 plus m2 tensor n2 plus mk tensor nk. What does it mean for that to be equal to another element of your tensor product, m1 prime tensor n1 prime plus ml prime tensor nl prime? Remember, for an arbitrary element, we can just take sums of these simple tensors, elementary tensors. We don't need to take R linear combinations because we can always take the ring element and absorb it into the first factor. Well, not surprisingly, given the discussion that's led up to this, what does it mean for these to be equal? It's a statement about bilinear maps from M cross N. This equality holds if and only if for every bilinear map be from m cross n to p, the sum from I equals 1 to k of b mi is the same as the sum from j equals 1 to l of b mj prime nj prime. So this gives some way to see that two tensors are not equal. If you can find a bilinear map for which you can see that this equality doesn't hold, then these two tensors are not actually equal. All right, so now we've talked about some basic properties and ways to understand tensor products. In the next few videos, we'll do some more examples and prove some more important properties.